Hello and welcome back to the Hyperthesis episode 74. Well, today we're going to be talking a little bit about communications and such and how we come to communicate as human beings. My name is Feely.
I'm Patrick.
And I'm Liam.
All right. Before we get into the meat, I believe someone has an intro topic.
Yes, I do. Which is not about, well, it's a little bit related to communication, but it's on dark matter. So I found an article that was published yesterday about a paper that was published 4 days ago, describing how dark matter may not exist at all, which is a bold claim. There's a lot of evidence that it does exist, but it's worth exploring different theories. So last year, a physicist named Rajendra Gupta at the University of Ottawa in Canada published a a semi-controversial paper that proposed that the universe was potentially about twice as old as we originally thought, so around 28 billion years instead of 14 billion years. And this came around the time that there was this recent James Webb telescope data, which it gave, the data didn't quite match what we expected to see. And by, I guess, didn't quite match, it was like vastly different what we would expect it to be in a lot of ways. And his idea was that maybe if the universe is twice as old, it helps support this data a bit more. And it was a popular discussion topic on YouTube, all in the scientific community, and we even talked about it actually in our podcast.
Well, yeah, one of the things is that the media kind of upplayed that a lot, right? Because the
Yeah.
speculation was like one line in the paper that's like, well, this could be. And it became something that's like on the headline, even though like the actual the material of the paper, like 95% of the paper is not about that exactly. Like it's not about that prediction, it's that tired light theory.
Yeah, so he revisited. So there are these older theories, and we talked about this in the episode a bit. But there are these two older and largely dismissed theories called covariant coupling constants and tired light. And kind of the very fast summary of what those ideas are is that the forces of nature, they actually change over cosmic time. They get weaker, and that light loses energy when it travels very long distances. So in standard cosmology, the accelerated expansion of the universe, it's largely believed to be caused by dark energy, which is this mysterious stuff we don't know anything about. But maybe this tired light and this covariant coupling constants, at least according to this guy and his colleagues. Well, I haven't actually checked if he had any co-authors on the papers, but I'm assuming he does. Maybe he doesn't. But anyway, this could be this could be another way to think about it. Instead of having this mysterious dark energy or something, maybe you can replace that with the fact that you have these covariant coupling constants and tired light. But anyway, I'm not 100% sure, and I'm sure there's more to it than that, and there's many physicists who would disagree, I'm sure. But I wanted to talk about this kind of second paper a bit more, to study where he studied dark energy. Or sorry, dark matter instead of dark energy. So he kind of took these same old theories, these theories, like he didn't come up with the theories. I think they were proposed a long time ago, and he just like revisited them and said, oh, maybe these can help explain some things. And he proposed that maybe dark matter isn't what we thought it was. Maybe there is no dark matter, and if you instead replace it with these theories, they can explain these gravitational effects that are missing that you can't describe with regular kind of gravity. So he published this paper 4 days ago that was called Testing Covariant Coupling Constants in Tired Light Cosmology with Observed Baryon Acoustic Oscillation Features. And it was in the Astrophysical Journal. And just a quick summary, that out of all the stuff in the universe that we see, only about 5% of it is regular matter. So like atoms and electrons and things like that. About 27% of it is predicted to be dark matter, which is this stuff we can't see because it doesn't interact with ordinary matter. It doesn't interact with light, but it interacts via gravity. So we can look at like the rotation of the Milky Way galaxy, for example, and we can see that there's a ton of mass missing from it that should be there to match the experiments. And then you can kind of say like, all right, there's this dark invisible matter that should be there. That's one big evidence for it, and there's more. But and then the rest of it, so 5% regular matter, 27% dark matter, and the rest of it, about 68%, is predicted to be this dark energy, which helps predict the expansion of the universe. And we've talked about all this stuff before, but in this work, Gupta replaces dark matter in the universe with this covariant coupling constants and tired light theory. And he found that if you actually do simulations with it, it matches what we see in the real universe. And I admit I don't quite know the full details because I didn't read the paper, but he kind of looks at how this theory has an imprint on the cosmic microwave background in some way. And it seems to match what we actually see, which, maybe that's a coincidence. This is one simulation. You'd have to do a bunch of simulations of very different things to make sure that it matched every part of what we see in our experiments. But he said, I quote, "There are several papers that question the existence of dark matter, um, but this one is the first one, to my knowledge, that eliminates its cosmological existence while being consistent with key cosmological observations that we have had time to confirm." End quote. So it seems that there's other people who've proposed alternate theories to dark matter, but this is the first one that actually, at first glance, seems to match one specific observation we've made.
Well, I think I was, this week I was almost convinced to jump onto the dark matter ship, because I've been a dark matter skeptic, I think, for a
Yes.
while. And even though there's a bunch of evidence for it, I was still, trying to find a way to, well, maybe there's other theories that could explain this. I just don't like the concept of having something like dark matter as a, as a solution. It could be a solution. It's probably our best guess, right? And it's very highly likely that it is, but now you're shaking my belief again. Now I'm ready to not jump ship. I was like, well, maybe they're actually, but the problem with that is that we kind of have to believe that the constants in the universe are changing, right? They're not exactly constant, and that is a kind of paradigm changing statement for in
Yes.
science, right? Like, well, maybe G, or like the gravitational constant is not exactly constant. Maybe it worked differently at different scale. Maybe it changed over time. I think we talked about it with, I think, was it Dirac that proposed it, and that constant change or whatnot, and that might be impossible to measure even, right? Because it's over a long time scale. Or is there a way, because like, well, I guess you can change it such a way that the simulation match the data. I mean, if you extrapolate from the data and then create a model of changing constants to match the data, it could work. And I wonder if there, because one of the criticism of this type of modification is that it only explains some of the explanations, not all of them. And the proposed dark matters is supposed to explain all of them.
Yeah, so that's the thing, is that this simulation he did, it matches one observation we've made about the cosmic microwave background. Apparently, I haven't read the paper, but I don't think he'd publish it saying it does if it doesn't. But that's a very large scale thing. So dark matter, there's different scales of it. So you have these things called dark matter halos. You can get lensing from dark matter. So what does his theory explain those things as well? And I'm sure there's some things that dark matter doesn't explain yet, but it seems to be kind of like the best guess, like you said, the best guess we have. It seems to explain the most things that we see regarding this strange stuff that interacts with matter, but not with light. Well, it interacts with it gravitationally at least. So yeah, I definitely think that I'm still not 100% convinced, obviously. I think dark matter's the best guess we have, so that's the most likely to follow. But it's definitely it's not worth ignoring just because you think one thing looks very obvious. It's obviously dark matter, right? It's definitely worth exploring the other avenues and seeing because back you could always just say, well, Einstein, for example, back in the day before quantum physics and general relativity, if you told someone that time was relative, they would just laugh at you and they say that makes no sense at all. That's so silly. Why would time be relative? Or why are superpositions in quantum mechanics a thing, right? So it's not unheard of for strange things to be legit. So it's good that this kind of avenue is being studied, but I think you want to keep studying it if you are seriously. I think he's going to keep studying it. Um, until maybe he'll find something that just does not match. And maybe that'll help. Maybe that'll convince him it doesn't work, or maybe he'll keep finding that it keeps matching experiments and it keeps matching the data. So who knows?
Yeah, I'm skeptical of this, but like healthy skepticism where if
Yeah,
it does keep matching, then that's very interesting. But I don't know, coming from a dark matter background, it would be very difficult to convince all the people working on that dark matter doesn't exist because there's a lot of good evidence for it, especially within the cosmic microwave background and looking at um, different anisotropic peaks from that. That's really solid evidence that there is something else there rather than just baryonic matter. Now, whether it's in the form that we predict, so a common dark matter candidate is the weakly interacting massive particle, or WIMP. Axions are also there, and a couple other things. But there is, I guess, some evidence that indicates that dark matter most likely does exist in the form of some sort of particle that just doesn't interact electromagnetically, which is why we have such a difficult time finding it. But I don't know. I feel like I would need to read this full paper to really understand what the author's getting into, but a little bit suspicious of it.
yeah. I think again, you know, it's a bold theory. Um, so of course, bold theories need bold evidence, right? But at the same, and it depends how he's going about it. And he's an experienced physicist. I'm assuming they're approaching it methodically, and usually the people, maybe I'm saying he believes it, maybe he doesn't believe it, but maybe he's just taking that path to like check and say like, all right, is this legit or not? Is there something that can be said here, or is dark matter the best thing still? And like Feely said, maybe they're taking data and they're kind of like fitting the model to the data. In that case, I'd be more skeptical. Or maybe they're taking like straight up stuff that was derived based on some assumptions and showing that the data matches it. Then that would be better in my opinion. But yeah, it's interesting, isn't it?
Well, one thing that's for sure is that to explain these phenomena, we need something beyond the standard model, whether it's be dark matter or like modification to cosmological constants or gravity. It's not a standard model cannot explain this.
But you see is that whatever's beyond the standard model, you then figure it out and then you just add it to the standard model. So that way you can just say the standard model is the most up to date version of physics we have. So I find that kind of funny that people talk about beyond standard model physics, but then usually in some way they might try and say like, oh, this we can add this to the standard model, so it's now just standard model physics. I don't know. It's interesting.
I would disagree with that just slightly because the standard model is a pretty rigid framework. And so this beyond the standard model stuff indicates that the whole, I guess, concept behind the standard model isn't correct. So we did make
Mhm.
like severe changes and we are finding stuff that breaks the standard model. Uh,
All the
they're
time.
still like, yeah, exactly. So standard model is definitely not the absolute like standard model of the universe and of particle physics, but um, I don't know. It's if we end up changing things and changing the framework, then I don't think it will still be called the standard model to incorporate everything.
I mean, standard models based on a few specific symmetric groups, right? And if it turn out we can use those, well, we need more to explain. Well, it's gonna be not standard model. That's how I understand it.
I think there's a but yeah, it's like the matter antimatter asymmetry is just like the most blaringly obvious violation. But yeah.
Yeah, I just listened to a talk about that. It's fascinating how people, because what you do, because one of the premise was that the standard model cannot explain this at all because it would put everything in equilibrium and there's no like CP violation or whatnot, right? And that doesn't work.
There are modifications suggested to the standard model that would allow for this antimatter-matter imbalance in the universe, but they get super complicated and I don't know. It's hard to test this stuff just because you need very sensitive equipment and high energies and a lot of observations. But going back to this dark matter thing, one final thing I want to say is it's good that we're exploring these different theories because a lot of people I've talked to in the dark matter world agree that if we don't really find WIMPs or even axions within the next 10 to 15 years, then we're going to have to look somewhere else. The detector technologies that we have today are quite advanced and getting more sensitive by the year. But we can only go so sensitive before we have to start saying, okay, we have to start looking somewhere else completely. So there's this kind of, not official deadline, but deadline in people's minds who are running these dark matter experiments saying, okay, if this doesn't work, if we run this for a long time and we can't see anything, where do we start to look next? And so these alternative theories, especially from the common WIMPs or axions, not so much machos, but it's good to look in other directions, which is what Gupta is trying to do.
All right. I think that's it for the intro topic in the interest of time. So
it relates to science communication a bit because, like you said, it was kind of like blown out of proportion that it's like this one-liner saying the age of the universe is twice as old as we might think. That's like the main thing that was communicated, right? So,
well, that wasn't what I meant when I said communication, but sure.
Oh, you meant like okay, I see.
Like the physically communicated.
Yeah. All right.
Well, yeah, I think because I know silent communication in that sense, in terms of imparting knowledge is very important. But I think we should chat a bit about how human actually physically communicates, not telepathically, as we all do, of course, or like cats do or something. I think they do, but so I think we grew up when at least telephone was around, right? Where we use a lot of, let's say, radio waves to communicate. But when we look back in the history, I think one of the earliest long distance communication has to be like smoke signals. I think that's pretty global, where people use smoke to communicate. Or lanterns or some kind of light source, and you can put a screen over it or put your hand over it. Like imagine the old movie where someone walk at night with a little lantern, and they turn it, put a screen on it and off it, send a secret signal. And that is was how people communicated back then. Maybe, and the message usually quite terse or very, very short. And they try to basically, be as efficient because it's really difficult to send some kind of information over long distance. Even though we have, I think further on, we have writing. Writing becomes, people start to write. You can send letters. But as the technology progresses, I think one of the revolutionary technology is the radio, which allow communication at the speed of light. And in a way, radio is kind of easy to make in a sense compared to, well, it's not easy technologically, but the principle is not difficult, right? You have changing magnetic field. And how do you create magnetic field? You put current through a wire, and you keep, it should keep turn on and off. So you change magnetic field, and that generate electromagnetic waves out. And if you do it at the right frequency, you can get a radio wave, or you can do it at a different frequency, you get auto waves. You can even get light from it, right? So I think that is really important to acknowledge that, well, before, we had Telegram, which is also very slow. I don't know if any one of us have ever used a Telegram, not the application, but like the actual Telegram. Or remember, I don't know. Well, I don't know if you guys do it here, like pager. I think it's a little bit before our time.
That was slightly before my time, for sure.
I mean, I will say pagers are used in hospitals to this day. So
not as much anymore. They say, doctors just now get people to text them instead, like their whole texting system from the hospital, because no one want to use pager anymore. And you remember, or other stories about pager, right? Because you want to page someone, you have to call into the call center. It's like, hey, page this person, and here's the message, and you have to say it out loud and to page someone. And that, you see in the shows or the medical show all the time, where it's like, oh, page doctor blah blah blah, this blah blah blah, and you tell the operator just typed it in, right? Because I remember the story on like, oh yeah, you're gonna page your lover, and you have to call someone on the call center and say these lovely messages.
It's also when, I don't know if you did this when you were a kid, but like you have a circle of people sitting there, and like one person whispers a message to the next one, and then they carry it on. By the time the message gets to the other end, it's like completely distorted and it's changed. It's like telling someone to tell someone something isn't very efficient, because they could misinterpret something, or over a phone they might hear the wrong word and information can get skewed. So I think it's just easier to like send it yourself, right? Now that we
That's why
can.
like in court, what's it called, a stenographer, where they can type like I don't know, many words in a second, because instead of typing like and, right, they press 3 buttons at the same time, and it would come out as words. So you can basically like playing piano, because you can play like in sequence, but stenographer, they use like chords.
Those are the special computers.
Special keyboards, where you can push in multiple buttons at a time, and it make a best guess of what that word is. And it's fascinating. I think you have to train for years or months to be able to do that. So the point I'm trying to make is that the communication in the modern world is quick. Like, we're online right now talking to each other with very low latency. And it's kind of crazy, because like if you want to send a letter home, it takes like at least days, right? And this kind of communication allows the technology to advance rapidly. Because imagine in the Einstein and Bose and all these guys, imagine you publish a paper. That paper has to go to a journal, or like a library, and they have to like do things and print it and ship it to the libraries around the country or the world, and then someone has to go through it, read it, maybe make some sense of it, maybe write a letter to the author like, hey, your work is great, can we talk about it? And then they would write back. But that could take over the period of like a year or two. But now we can send them an email, and maybe they will answer next day, and let's hop on a video call. And this type of, well, what do you call it, latency, has been minimized through technology. And be able to do that like by actually spending billions of dollars laying down wire under the ocean, right? And use and especially the technology of fiber optics to use light to basically encode our information into light and send it to our fiber optical wire. To me, that is very fascinating.
I will just say, for more on fiber optics and to learn more about those, you can listen to our introductory topic on episode 49, How Old Stars Can Get. We go quite into depth in the fiber optic network that we have. I mean, there are over 1.4 million kilometers of cable just lying on the ocean floor that are solely for communication between people. It's just insane the amount of infrastructure we have just for communication, and that's not including all the radio communication that we have, which is ramping up quite a bit, especially with things like satellite internet becoming more and more popular, especially the one that's produced by SpaceX, which I believe is the only publicly available one. There's probably some government ones that are used to communicate. But even those using sat phones, so for example, we have to use them when we go out into the field, or if you're in a very remote place, you use sat phones to communicate, and they still rely on radio waves to communicate. So aside from these undersea cables and these fiber optics, radio is incredibly important for communication.
Yeah, and it's easy to receive too, right? Because they are basically electromagnetic wave that you send it to the air, and be around, and then all you need is some kind of antenna, right? Some kind of, even back then, antenna, I think it was look like a circle, a loop, because when the electromagnetic wave passed through it, it induced very small current, and you can measure that current, take the signal from it, interpret that signal, and then there you go. And we have been doing that for quite a while. You go on your car has antenna. Sometimes it's hidden. Now these days, really, people don't really know where, sometimes even where the antenna is, because it's sometimes built into the windshield. I think is those kind of sticker-like thing. Because all you need is some kind of not exactly loop, right, but some kind of geometrical structure that the current can be induced upon.
Because I think older antenna on cars, the big metal ones, they had to be that big in order to pick up the radio frequency. You can think of like the radio frequency hitting it and it vibrates, and then it gets your signal. That's not quite what happens, but now they've made the doesn't vibrate, but that's like
I mean, it's okay, it vibrates, but not in a mechanical sense, right?
Yeah,
but
like electromagnetically.
In terms like, yeah, like the potential vibrates in a sense. You think, yeah, it's vibrates magnetically, right? There's some things being induced there.
That was one of these things that I didn't really appreciate until grad school. I feel like we were taught it, but it didn't really click with me until I was more experienced. That I always say this all the time: small things interact with small things, big things interact with big things, but small and big things don't necessarily interact with each other very well. Things need to be the same order to interact with one another, and that's why these old antennae used to be so big, is because they had to be. But now that we have the technology, they can make them very, very small, and they figured out ways that you can pick up these signals so that the radio waves interact with them. So all of physics just comes down to that in my mind. Things interacting.
One of the problem with the modern mobile phones, where they want to make it smaller, or want to make it all plastic or whatnot, but they still need to pick up the phone signal. That's why I think some of the phones still have metal rims, because they actually use those as antennas.
Well, I mean, if you have an iPhone, I think like 6 or earlier, or one without the full display on it, and you still have that button on there, you'll find plastic lines, because it's important for phones not to have a metal casing where the antenna lines lie. So with these older iPhones, for example, they have plastic lines throughout that are aesthetically pleasing, but they are there out of necessity. So it's kind of form from function, because you need to be able to transmit these signals. Same with a lot of other phones. If you look along the rails, chances are the sides of your phone might either be glass or plastic. And again, that's for the transmission of these signals. Because one of the important things is that you can't transmit these radio waves through metal. So things like even if you wrap your phone in aluminum foil and try and call it, it's not going to be in service. It's going to lose all its signal. This is why we have giant or small structures that are known as Faraday cages, which, again, as Liam said, similar things of similar size will interact with each other. But if you are able to, say, make a Faraday cage, which has holes that are smaller than the intended signal that they want to filter out, they'll block that signal. An excellent example is in your microwave, which I'll just add that a lot of radio waves that we are talking about are actually microwaves. There's in communications and other areas, there's a lot of overlap between the two in terms of the wavelength. So we might be saying radio waves, but realistically, your phone is not able to transmit a radio wave. It transmits microwaves. But it's just known as radio because of how it's classified by governments and regulation agencies. But your microwave has this Faraday cage, so you can still see through it, but the holes are small enough, and it's all made of metal, that the wavelengths of microwaves can't actually pass through the cage and stay inside and heat up your food.
I thought the newer phones, they use the frame itself as the antenna. That's why it's metal. Maybe I'm wrong. But especially 5G, because I heard the fifth generation is kind of hard to pick up. That's why older phones like what I have cannot use 5G. And I see anything that's released after my phone, they all have metal rims, not just case, like the borders. I'm talking about the Apple products. But I think that's to pick up 5G.
Maybe that'd be a pretty smart way to do it if that's the case, right? Because you've incorporated it into the case, that saves a lot of space. But yeah, 5G, it's higher frequency radio waves, right? I'm getting that correct? I don't know.
Well, I'm not exactly sure. I think it might. The thing is, people would. I think
I think it is.
The name is misleading because 5G doesn't mean 5 gigahertz, right? It's this fifth generation. 4G is fourth generation.
But I think the idea is that because it's higher frequency, you can do more with it. It's better. But because it's higher frequency, it now means you need smaller components to pick it up, or you need to be more clever.
No. The thing is, higher frequency you can encode more information.
Yeah.
But it doesn't go through like obstacles as well. Like for example, like the radio, you can have a radio tower, and then it can go for miles, right? But if you have 5G tower, especially in the city, it doesn't go that far. So you have a lot of towers. So this is why it's like it costs more, but it can transmit a lot more information.
And I think that's where this original, the meme about, the 5G waves and stuff, like I think that's where that kind of came from, is because some scientist somewhere probably said if 5G is a higher frequency, it doesn't travel as far. And there could be some concern that it interacts with the human body a little bit or something like that. And then maybe that was taken too far out of context. I don't actually know.
Well, there was this idea that it interacts with like, was it that in the same range of frequency of our brainwave is gonna change our brain? But the intensity of the wave is like minuscule, right? And we experience radio wave every day from space. We have the cosmic waves coming down, right? And yeah, to me that's a little ridiculous.
Yeah, and there's, like you said, so many radio waves going through you at any given moment, and there's electromagnetic waves hitting you all the time, and I mean, obviously it's something to think about, but I don't think, I'm sure you can do a test that proves if it's dangerous or not, right? And I'm sure they've done it.
I'm sure they have done it, right? Like
Yeah,
there
yeah.
is no way we haven't tested that. Like for example, I think is the radioactivity. Um, is when they found it, it's really catastrophic to human body if it's, you exposed to it, right? Marie Curie was, she got affected by it, and I'm sure with multitude of people, and that's pretty clear. But I don't think we have seen any evidence that the radio wave from phones, if it's you don't put your hands in microwave, for example, that because that's pretty dangerous. They are not really affecting us. They just go through us. That's why we need antenna, special device to pick it up, or it would just go through us and does nothing.
But anyway, back to communication. So I'm just what do you have prepared next to talk about now that we've
Well,
gone on a big tangent on phones and radio waves and 5G brain waves and
right. So I think I want to talk a little bit about the future of communication, because now, like, we are almost at the point where we communicate at the speed of light, or we are communicating at somewhat the speed of light, right? And now it's just like, well, what's the shortest route? We have cables in the ocean, or we have satellites where we just send out signal there. But I think the future that's coming somehow, maybe it won't happen, is quantum communication. So can we use the concept of quantum entanglement to communicate?
in theory, yes.
Do you know anything about it?
I should. I'm TAing a quantum information class, but turns out I don't do quantum information. But if you know quantum mechanics, you can do quantum information and encryption and things like that. Yeah, I know that in these assignments I'm marking, there's a lot of questions asking the students about, like, if it's like the basics of encryption. It's like if I send a message in the form of a bit, and different spin flips do different things to it, what information can I get out of it? So I think the theory of quantum information is pretty well established, but it's just making it happen, because the moment your quantum system interacts with something, it decoheres and you no longer have a quantum system. So, like, creating quantum communication is hard, but I think in principle, like, we know how it works theoretically quite well. It's just we have to be able to create something that can do that.
Because I wonder, well, I mean, I think we are talking on a different view here, because, well, that's more like on the information itself. I'm talking in terms of as a means of communication. For example, right, like historically, we went from really slow, from smoke signal is quite slow, right? But um, well, also it begs the question: what does it mean by fast? Because can we use quantum communication to break the barrier of the speed of light?
Don't think so, because there's that whole, like, entanglement argument that
Yeah, the
you,
myths.
yeah, the
Right?
mittens and the whole, like, you measure one state, so you instantaneously know the other state across the universe. Um, spooky action at a distance, but the person across at the other end of the universe, you can never tell them that information faster than the speed of light. Um, which is something we've mentioned before. We've talked about entanglement and such things. And I'm no expert on this, so I'm kind of hand waving my way through it. But
Yeah, I mean, this is something that's popular in sci-fi. The one that comes to mind is Ender's Game, where they use this device to communicate instantaneously with an army fighting an army of bugs. It gets confusing at the end. Sorry for the spoilers. But there's this idea of like using quantum entanglement to communicate so quickly, but it is still limited. And there are some different theories that might allow for faster than the speed of light communication, but of course, trying to prove those is pretty much impossible. We have a very solid understanding of how we can communicate, and while we are able to increase the distance in which we can have two entangled particles, So there's been experiments on Earth and then in space or across the Earth of looking at how entangled particles actually behave. Actually using that information is impossible.
Well, I think one way is, well, not to circumvent the speed of light is the Alcubierre warp drive, right? Like warp drive, you just shorten the distance. If you can find a way to shorten the distance.
Now that I've been learning a little bit of Spanish, I found out that it's actually pronounced Alcubierre. So it's like era at the end instead of Alcubierre, because everyone says Alcubierre warp drive, but Alcubierre is a Mexican guy, so, or at least he has a name that's pronounced correctly in Spanish. So yeah, Alcubierre. But yeah, so warp drive. Oh, now we're getting. If imagine that you could develop warp drive, but you didn't use it. You couldn't use it for traveling, but you could use it for communicating. You could open a little tiny like wormhole and you could fire like a few bits of information through it or something.
That's more likely, right?
Yeah,
Because
that
to
is more
send mass
likely.
to it, because send photons is massless. This might be easier to send.
Yeah, and I would imagine it would be easy, like creating a massive wormhole to send like, a spaceship through. That would be. Yeah, it turns out you need a lot of energy to make a wormhole. So if you can make like a little tiny, like atom-sized wormhole and send some photons through it, I don't know the numbers, but it's more viable to me than sending a spaceship through a wormhole.
I mean, you show me exotic matter or negative mass objects, and I'll believe you. But until then, I think we're definitely limited by the speed of light.
Yes.
Yeah, apparently negative mass is not well defined, right? At all. It's not charge. Charge can have negative charge, but mass is. Yeah, I have a little talk about negative mass with the speaker last week that came talk in a colloquium, like antimatter. Is there a reason why it doesn't have negative mass? I think it's a fair question to ask, and what's the answer is that, well, negative mass is not exactly well defined at all. What do you mean by negative mass, right? And it's like, well, exactly, what does that mean? And so, but that's another can of worms.
Yeah, you start getting into like symmetries and how antimatter, like you have this, I forget how it works, but you like negative charge on an electron, for example. That's some kind of symmetry that the electron obeys.
Oh, there's a quantum number, right?
Yeah. So for like massive particles, the anti-charge of mass would be negative mass, maybe, and then you'd have like repulsive gravity. But we don't see that or haven't seen it.
Yeah, and also mass is not a quantum number, so it's a completely different regime.
Yeah, as far as we can tell, it's not.
Exactly. Yeah, but I think in terms of that concept of getting signal from like some kind of hole, wasn't there in the 2001 Space Odyssey? That's how they kind of found that little wormhole, right? They got signal from the hole near Jupiter. It's a spoiler, but if you haven't seen movies from, I don't know, many years ago, it's fine. It's spoiler friendly now. It's been years, decades. So
1968. Yeah,
1968.
I've somehow never seen that movie.
Well, you need a lot of patience to see that movie. It is a fantastic movie. I remember watching it for the first time. I was like, I don't get it. And the second time, I was like, wow, this is amazing. So when you're young, you're like, dude, it's so slow. But so I think the second point I was going to make is that, what do you mean by speed? Because since we use the wave, electromagnetic wave to communicate, it's always going at the same speed of light, right? But somehow we're able to speed up, quote unquote, our communication. And what does that mean? Well, the point is, even though the medium that we use to carry our signal move at the same speed, like speed of light, how much information can we encode in a period of time? For example, 1 second. if you use higher frequency, imagine there's little higher, more undulation, right? Up, down, up, down. So we can encode more information into 1 second. That's why having higher frequency allows us to encode our information into more information into 1 second. That's why we want to have higher frequency communication, even though the medium is actually moving at the same speed. I wonder what the future is going to be, because the frequency of the electromagnetic wave is, well, it determines not only, well, how fast it go up and down or in the magnetic or electric field, but its energy, right? We all learned about the photoelectric effect, and it could affect people when it's too high of energy, but radio is low.
I mean, I think the future of communication will not see an increase in energy or an increase in wavelength, but very minute changes in wavelength, where we have slightly different wavelengths communicating even more data. So something like 5G, where we're able to fit more information in the radio waves or microwaves because they're literally oscillating faster. Whereas I think in the future, we'll see something which reminds me of three-phase energy transmission, where we have multiple phases of energy that are at different phases that are actually able to deliver more electricity more consistently. I think we'll see something like that, where we have this kind of multi-band approach with everyday devices, because they already use this in something like fiber optics, where they're using slightly different wavelengths of light to transmit just a lot more information through fiber optic cables. I think we'll see something similar, where we aren't dealing with speed of communication, but more so the bandwidth of that communication.
Yeah, the keyword I was going to say is bandwidth, right? Because, well, you can have, let's say, it's like a parallelizing communication. So if you have one frequency, there's only so much you can transmit. But what if you transmit two frequencies at the same time? How about 3? How about 4? Let's say you have a range of 2 to 2.1 gigahertz, right? How many bands can you send? Let's say you can distinguish within 0.01, right? Then you can send like 9 or 10 bands. And the more precise you can make out the distinction between frequency, the more you can parallelize the transmission of information in the same band or in the same range of frequencies.
Is this just like Fourier series? You send a signal and it's composed of many different. You send a signal, it has like one overall frequency, but it's composed of many, many different smaller
like overtones,
frequency waves. Yeah, like how in music, the timbre. I don't know if that's pronounced right, but
timbre.
It's
timbre.
But I've heard it. No one pronounces it. I've heard it different. But anyway, all right, the timbre of the instrument. So how I can play piano at some frequency and I can play guitar at the exact same frequency, yet they sound different, and that's because they're composed of different amounts of composed of different frequency waves to create an overall frequency that's the same. Is it similar for this communication stuff? I don't know much about it, but like
I don't think so.
You could encode a lot of information in a single wave just by summing together a bunch of different waves into one. Is that something people do?
Well, in a sense, let's say I'm telling this information at 2 gigahertz, 2.000, right? But I can send along the another information at the same time at 2.1 gigahertz. And then, but if your receiver cannot distinguish between 2 and 2.1, it's going to be scrambled.
Yeah.
But imagine, because if you can have multiple, I think they call channels, right? You can have in a frequency or a frequency bandwidth, the range. Let's say I reserve 0.9 to 2.1, and I'm going to split that into 20 channels, right? And each channel is going to have 0.1 bandwidth. And within that 0.1, I can send a signal that, let's say, 2.05 or 2.06, and that's going to be counted as one channel. So you have uncertainties that you can operate with in terms of the frequency uncertainty. But the more precise we can be in terms of our instrument, the more we can split it up. I think that's one of the reasons we go, well, the generations in wireless technology work. Because I think before we can have that many channels on the same frequencies, and the higher channels you can have, the more parallel transmission you can do, and that is like, and it speeds up by like the order of magnitude of, right? Because now instead of one channel, you can have two, and you have 10 channels. It's 10 times faster than having one channel. But if you can distinguish between channels because your instrument is too crude, then that's trouble. I don't know if I understand this correctly, but I think that's how it works, and the physics kind of makes sense. All right. Well, unless anyone have the lasting comments about the physical communications that humans have been using, we're gonna end our main topic here and let Patrick tell us how to contact the hyperthesis.
Absolutely. So there are many ways in which you can communicate to us and in which we like to communicate to you. The first being our email. So you can send us an email at hyperthesispodcast@gmail.com where you can ask us questions, or you can comment and let us know, especially if you're a communications expert or a quantum communication expert. We would love to hear from you and even have you on the show. You can also find us on Instagram. We are at the Hyperthesis, where we post updates when we post episodes, as well as some other additional content. If you want to listen to us, well, congratulations. If you're hearing this, you'll be listening to us already. But in case you don't know where to find us, we are based out of Spotify, but we are also on Apple Podcast, Google Podcast, RIP, Amazon Music, Overcast, Castbox, wherever you get your podcasts, we are there. And if you happen to get your podcast through a service that you can rate us, feel free to leave a rating and a comment. We love feedback. We would like to know what topics you're interested in. So if there's a topic that's been bugging you, you want to find out more about, and you want to hear us talking about, send us a communication some way or another. We are also on YouTube. You can find us on YouTube, just search the Hyperthesis Podcast, where we have these excellent animations. And the first person to tell us what the new animations look like for this season's episodes, well, you'll get a shout out from us at some point. So go ahead and check out our YouTube and feel free to give us a like and subscribe. And again, comment the topics that you would like to hear. And again, if you are an expert in your field, we would love to hear from you, whether you are a grad student, a postdoc, a professor, someone in the industry. We are more than happy to have you as a guest on our show to talk about an interesting topic in science.
All right. So we have the story for today. Take it away.
Well, on the topic of communication, there is a very deep and rich history of how people communicate. Now, trying to communicate globally has been a challenge for centuries, as Feely mentioned early on in the main topic. And as more regions have become interconnected through trade and colonialization, which was not particularly great for about half the people experiencing it, it necessitated the communication between different places around the world. Now, there has been evidence of very fast communication that happens through local communication networks historically. One of my favorite examples is that in the Eastern Roman Empire, they were actually able to pass messages through a series of lighthouses, ranging from Armenia and Syria all the way to Istanbul, which at the time was called Constantinople. And this happened at a speed of over 700 kilometers per hour, which, given that this was thousands of years ago, is incredible that they were able to pass messages so quickly using essentially just a series of shining lights. Now, there have also existed extensive relay networks that allow for essentially fresh or fast horses to be used that run between relay stations, are switched out, and so messages can move along quite quickly. Now, not at the rate of 700 kilometers per hour, but you could certainly move more advanced messages. There are also cases in many different civilizations of either the equivalent of horses being used and relay stations, or even people who could run fast. I believe it was the Aztecs or the Mexica who had outposts essentially every mile and had their fastest runners relaying messages between those different outposts. Now, as a kind of more personal anecdote, in Nova Scotia, we had a famous sailing ship known as the Blue Nose, which is a type of schooner. And schooners were specifically developed to be fast deliverers of important messages and mail. Now, schooners were developed kind of beyond the point where they could carry meaningful cargo and became racing ships, but these were the original purpose, including sailing ships like the Blue Nose. Now, with advancements in electricity research, it soon became possible to send messages other than physical means. And so what I'm talking about is using electrical signals to send these messages. So these signals could be sent along very long lengths of copper wire by just changing the voltage. So you could go between a high voltage and no voltage, and that could be read. Now, thankfully, we had people like Morse working on this situation who actually was able to produce a language that could be easily conveyed and written after very little training through these systems. Now, these were known more commonly as telegraphs and were able to communicate over very long lengths of copper cabling. Now, a place where I've been before on the western coast of Canada on Vancouver Island is called Bamfield, and this used to actually be the terminal of, or at least one of the terminals of the Trans-Pacific Telegraph line. So essentially there was this incredibly massive, thick copper wire that spanned the length of the Pacific Ocean, and we were able to send signals across from that. However, the physical telegraph was still quite limited, and it's very interesting because in the kind of museum they have at that center, they show what the signal looks like when it leaves the station versus when it arrives at the other end. And it gets quite damped down, it's hard to read. You really need to know what you're doing to understand long-distance telegraph communications. Now, as we have mentioned over the course of this episode, we've really highlighted the use and the need for radio communications. Pretty much anything that you are using that connects to something else uses radio. Now, there is, of course, fiber optics, which don't really use radio signals, but other than that, you are using a radio signal. I want those of you listening to think, do you have a landline? Do you know someone that does have a landline in their house? Chances are they might be older, and chances are you yourself do not have a landline. Now, you might, but even then, if you don't have a landline, you rely on radio signals. You're relying on your cell phone to text with people, to access the internet through a Wi-Fi router. All of these are radio signals. So I think it's important to mention the person who came up with radio or is said to have invented radio, and that's Guglielmo Marconi. So I'll just refer to him as Marconi, who was an Italian inventor and electrical engineer, and he was known for his creation of radio waves and radio wave-based wireless telegraph systems. Now, this was a very important problem around the turn of the century, particularly the 20th century, where telegraphs were good, but they weren't great, and we wanted better ways that didn't require these extensive cables that didn't always produce a reliable signal and were vulnerable. Especially in the early 1900s, there was a lot of fear of war, especially within Europe. So they wanted something more reliable for communication. Now, Marconi is said to have invented radio, which we'll get into in just a minute. But I would like to address the kind of controversy around that, as Nikola Tesla most likely invented radio first, and actually held patents for it in the United States. He did apply for patents after Marconi was able to apply for patents in the UK, but there's some controversy around that. I acknowledge it. We're going to move on and just focus on Marconi for now because he did make great developments for radio communication. So he was actually born to Italian nobility in Bologna in April 1874. And he was the second son of someone known as Giuseppe Marconi, who was an Italian aristocratic landowner. So he was born into power, and he also had an Irish mother named Annie Jameson. So there were also connections kind of with the British Isles. He had some siblings, and he grew up not attending school as a child, nor did he actually get a formal higher education. Instead, he was able to learn chemistry, mathematics, and physics from home through a series of private tutors, which, of course, was common for kind of the aristocratic nobility people around that time. Now, through these tutors, he was able to learn at kind of his own rate and was able to actually travel to see different tutors. A noted important mentor was Professor Vincenzo Rosa, who was a high school physics teacher from Livorno. But at the age of 17, Rosa was able to teach Marconi the basics of physical phenomena, including new theories on electricity, which at the time were really quite new, considering Maxwell had just come out with the Maxwell equations. Now, again, Marconi didn't have any formal education, but he did interact with a lot of people, including a student of Heinrich Hertz's, and this allowed Marconi the opportunity to attend lectures at universities and also to use a university's laboratory and library. Now, from a young age, Marconi was interested in science and electricity, and in the early 1890s, he began working on the idea of wireless telegraphy, which was the transmission of telegraph signals wirelessly through radio waves instead of using these wires. So he did a lot of research into conduction and electromagnetic induction and even some optics, but none had really proven great until a form of radiation known as Hertzian waves, which we will now refer to as radio waves, started to become more common, and the idea of producing them became easier, especially with advancements in electricity production. So at the age of 20, Marconi began to conduct experiments in radio waves, building much of his own equipment in an attic, and he used his butler for help because, again, of course, the aristocratic people had these services for them. So Marconi was able to build on the idea of Hertz's original experiments and began using what was known as a coherer, which was an early detector based on work by the French physicist Edouard Branly, and also used in Lodge's experiments. And what this device did was it changed its resistance when exposed to radio waves. So he was able to take this coherer, as it was known as, and in a first test actually made a storm alarm that consisted of a battery, the coherer, and an electric bell. And so what it would do was it would pick up radio waves generated by lightning to alert you that a storm was nearby. Now, not too much longer later, in 1894, Marconi was able to demonstrate a radio transmitter and receiver to his mother. So he was able to make a bell ring on the other side of a room by pushing a button from a transmitter that would then go to this coherer receiver and ring the bell. And this was kind of a form of communication over radio. And essentially what he was able to do was he was able to take this idea and he could achieve a much greater range by raising the height of the antenna. And so by boring some equipment used in wired telegraphy he was essentially able to set up this tower, which could transmit signals, set up another receiver about 3.2 kilometers away, and send a signal over it. Now, I won't get into too much more detail because that's all I want to discuss is just the initial invention of this radio. But he was essentially able to send signals over distances using these radio towers over radio signals and refined it more until we were actually able to get wireless telegraphy and send Morse code, for example, over telegraph systems. Now, the rest is kind of history, where telegraph systems were the main method of communication for many years. And I think just within the 21st century, they've shut down the last telegraph systems, which I believe were in India. But they went on to last well over 100 years, which is quite astounding. And we've had many pivotal moments, including the transatlantic transmission, which I do believe was a heritage minute, which is something that we have in Canada, where it happened on Signal Hill in St. John's, Newfoundland, which at that time was part of England. But they were able to use a 500-foot kite-supported antenna to receive a signal all the way from County Wexford, which is just quite the accomplishment. And that was only 123 years ago. So really not too long ago. And now we have our fiber optic cables. We have no need for telegraphs anymore, but we have an incredible need for radio communication. And it's thanks to the work of Marconi and Tesla and the many other physicists and scientists who came before and after them that we are able to send a message to a friend anywhere in the world, no matter where we are, and be able to communicate effectively.
All right, thank you, Patrick, for the story. And I can't believe I didn't bring this up as an example of communication. I was thinking, the warning beacons of Gondor.
Well, that's what I was thinking of when you said with like lanterns and stuff. I was like, oh, like I know that's in Lord of the Rings, but I think is that people have done that in the past before, right? They lit actual beacons to like communicate over distances.
Yeah. The one from Minas Tirith to the White Mountains to Rohan. That's like, well, that's for the Tolkien nerds out there, but that's one good form of communication back then, I guess. With that, I think we will end the episode here. Thank you for tuning in, and I will see you guys next week. Take care.
Bye, everyone.
See ya.